Okay.
How's it going? We all well? Right. Just get set up here. So, today, I don't have my clicker plugged in to your laptop.
Do we have a button? No, not yet. I might have to assist you with that as well, Nick.
All right, so thank you so much. So what we want to talk to you today about is managing failure in a distributed world. So we're going to kind of look at some of the patterns that you can use to manage all of the problems that distributed systems have. And some of them are not so complicated. But I think, it's an interesting area, certainly something that fascinates us. As Ricard said, do we all have our beers, wines, spirits, sangrias ready? Okay, so let's begin with a story. So this story begins back only a couple of years ago. So I was working on a system, and the system was for a brand new cloud migration. Nothing complicated there, right? As always, pointy head boss phones me up, says, so hey Nick, really excited about the launch of the new system. We've spent a lot of money on this, that typical passive-aggressive behavior that you would expect. He's like, we can't wait for Emojify to go online. We've got the big advertising coming out, premium campaign right in the middle of, well, it was Downton Abbey, which some people watch, but it was a big deal, right? I'm like, yeah, I'm confident. We've tested this. He's like, remember, we've invested big money in this. Again, pretty passive-aggressive. I'm like, well, yeah, we've spent a lot of time on this. We've prepared. We're doing our absolute best to get everything over the line here. And he's like, great. Don't let me down. Context behind that? You better not let me down. Of course, I'm like, hey, don't worry about that. The site's going to be rock solid. We've tested this to the ends. And then later that evening, so I'm sitting around, my colleague, we're in front of our computer, and I kind of see the spike in this traffic. And this spike is looking slightly larger than the figures that marketing had given us and the figures that we designed the system tolerances for. So I'm like, oh my God. My colleague's just like, yeah, I think this is going to break. And then, you know that awkward silence, right? What were we looking at? Well, we were looking at that. How long do you think it took between that and my phone ringing with this? That wasn't very long. So the boss is like, well, hey, so this rock-solid website you built. I'm like, let me explain to you cloud. So I'm Nick Jackson. I work as a developer advocate at HashiCorp, and I'm a pathological liar. This is my colleague here, Eric Veld. He is a PEBCAC expert. So let's talk about reliability. How did we get here? So we need to think about modern systems, because when you're thinking about reliability, many of the problems that you face today are based on the fact of where we've moved from and where we've moved to. So with traditional systems, when you're dealing with a monolith, everything was running in process. So you're making a call to a function. It's happening in memory. It's happening on the same CPU. the worst you had to deal with is kind of multi-threading, and that was mainly developed and handled by the programming languages. We moved to microservices away from monolithic systems because things were just getting bigger, complicated, higher demand. We needed a way to manage these larger applications as teams. We needed to sort of have a smaller domain model. It's getting too much for a single team to understand the complexity that's going on in modern systems. And importantly, we needed a way to scale. You know, the first system I built probably had maybe 3 users, and it was fine. You look today, and you're thinking millions of users, or thousands of users, hundreds of thousands. It's just more. Everything is on the internet, and you know, trust me, the users of your system, they're the ones that you should be sort of looking at with suspicion, because they're the ones that break it. It's not your code. Remember that, people. It's the users, not your code. But you know, microservices introduce some wonderful things around this scale, but what you're doing is you're breaking up your application. You're no longer having the ability for in-process calls. The calls are now happening out of band. They're happening across the network. And where this starts to cause problems is literally that. It's the network. So if we look at some of those things, and this is not something I'm telling you, this is widely acknowledged. Microsoft wrote a paper, you can find this on the internet, called Gray Failure, the Achilles heel of cloud systems. And they looked at a lot of the problems that they were having with Azure. And one of the things that they ascertained was that most of the things are not hard failures, it's transient failure. And it's transient failure which is kind of due to these factors. Performance degradation. You know, you got load in a particular area of the system. Just random loss of packets across a network. Flaky I/O. Memory pressure. You know, all sorts of things. And when we start to deal with this, we need to start looking deeper into some of the patterns that we can use to avoid these, because we can't get rid of it. It's just the nature of cloud. And some of those reliability patterns, service discovery, load balancing, retries, circuit breaking, rate limiting, we're going to look at these, and we're going to hopefully show some demos. Hopefully, right?
Yeah, I think it's working.
Oh, okay, cool. Did you detect the confidence in Eric's voice?
Uh-huh.
All right, so, and what we also want to look at is some not-so-common patterns. You know, some of the things that people who are operating at extreme scale have to deal with, but things like multi-cloud failover, geographic routing, you know, very real problems. And we'll take a look at that as well. So how are we going to implement this? So what we want to try and steer you away from is the concept of the fat client. You want to be able to externalize reliability rather than embedding it inside your application code. You know, this was a perfectly good pattern. Hystrix was hugely popular in the beginnings of microservices, but even Netflix have started to move away from that Hystrix pattern where you have libraries managing reliability inside of code, and they've started to look at externalizing things using different approaches. Why? Well, different libraries for each language, different implementations of the libraries. A retry in Go might not be the same as a retry in Java. Different configuration patterns, the complexity of developers having to implement this in every single service. It's just not efficient. We should have a drink now, because service mesh is another thing you hear a lot of, but the key thing about the service mesh is that it allows you to externalize reliability. It gives you the capability to have central configuration, and companies like Lyft really have started to pioneer and push this. The architecture is actually relatively straightforward, and we kind of have these two predominant concepts. We have the control plane and we have the data plane. So the control plane, that's where you're going to interact That's where your configuration is stored, and that configuration is automatically pushed out to your services to a data plane. The data plane is that externalized reliability. It's sitting alongside your application as a separate application. So all of the traffic that flows through your network is now going through these data planes, which are configured centrally. The control plane, feature-wise, we're looking at things like that service-to-service communication policy. So we're not talking about security today, but security is also another factor of why service mesh. Observability, absolutely essential when you're dealing with reliability. You cannot have a reliable system unless you understand the problems and the pressures that the system has. Service catalog, essential for load balancing in dynamic environments, the ability to automatically sort of configure TLS and again, give you that sort of encryption in transit. And most essentially, the centralized configuration of those data planes. The data plane, that's handling those reliability. It's that externalized component which easily allows you to sort of create this capability inside of your system. It's going to be doing all of those patterns, the retries, the circuit breaking, all of that sort of wonderful stuff. And the benefit, zero code change. The pattern which you'll see quite often when you're looking at that data plane is this one here, so a sidecar pattern. And don't think that a sidecar pattern is purely limited to Kubernetes. The sidecar pattern is applicable to virtual machines, bare metal, anything. It just means like a buddy application for your sort of main service. This is an architectural diagram of how we would sort of set that up in a Kubernetes cluster, but basically we're going for redundancy. We're going to have redundancy in every node. We have our centralized control plane, but our services, you can't see it on here, but each service has its own data plane, one-to-one relationship. So our application, pressure's on, Eric. So what we're building, we've got an example multi-tier application. We have an API gateway, and we're using Ambassador API gateway for that. We've got our website, which is React.js, pure browser-based application. We have an API, standard sort of Go API, which has a side cache, and it has a face detection capability. So a user uploads a photo to a browser, it goes through the API, we detect the faces in it, and we replace them with emoji. $1 million idea.
Should we give it a go? Fingers crossed, right? So let's take a picture, right? So this is one we did earlier on above, because he couldn't be there. He's
so
smiling
big,
up at us.
anybody who's watching and wants to kind of troll my good buddy Misha on Twitter, please feel free to do so. You have his consent.
So I have another picture. Oh, is that about the demo? So,
Thank you.
you're welcome. Maybe you want to take revenge and break things?
So we want to demonstrate how this is working for you. So one of the things that you find is that when you start to look at the implementation of reliability patterns, the first thing that you need to think about, you cannot do reliability without observability. Remember that. That is an absolute foremost. If you don't understand the pressure and the errors and the things which are going on inside your system, how do you performance tune it? The two go absolutely hand in hand. And the second thing is you've got to think of it as an iterative process. It's not a one-stop. You don't just configure reliability patterns when you deploy a service, because, again, system pressure changes over time. You've got to take an approach where you're observing, you're implementing, you're checking that the changes have got beneficial and then you're repeating it. And this is an ongoing process. Again, not just on that initial configuration, something that you want to constantly be monitoring. Step one, this should be common kind of knowledge, but load balancing multiple instances. It's the sort of the primary step of when you're building redundancy in a system. Never have a single instance of anything. Because a single point of failure, we're building distributed systems, so we need distributed failure as well. Let's see how we can make this work.
I think the blue one is working.
The blue one.
In the light, it's a little bit difficult to tell which LED is on.
So what I have here is the simulation of your users. This is Whack-A-Pod. And what it does is exactly what your users are doing, which is breaking your systems. It's a highly engineered piece of equipment. Unfortunately, it was engineered by mechanical engineers, not electrical engineers. Let's see if this works.
So we can see here on the left side. Can everybody read this, or should I make it bigger?
Bigger.
Bigger, okay. We'll make it bigger. Oh, wrong one. Is that big enough? Okay. So we see that we have one instance of the Emojify API running. It's healthy, right? The users are not misbehaving. But Nick has buttons, and they break things.
That's what the users are doing to your system all day long.
Right?
Breaking it.
There goes the pod, right? So if we try to do something, broken. Oh, where's slides?
So simple. Just scale up the number of pods, right? Easy.
Should we do that? How do we do that, Nick?
Not so easy. You have to think about a few concepts. Simply scaling is not just a thing. You've got to be thinking about load balancing. If you're working purely in Kubernetes, load balancing is a thing that you don't have to think about anymore. But if you're working with virtual machines or you're working in a more traditional cloud environment, it is something that you have to think about. The traditional pattern is just to use a hardware load balancer, but things have evolved. You're working in dynamic environments, you need more sort of different patterns to think about, and that's software load balancers. Because software load balancers have got the ability to be configured dynamically. They can look at the health of your services, they can read what's going on in your environment, and they can reconfigure themselves. But again, software load balancers can be costly. We need to sort of level that up another step and think about it. So we can do server-side load balancing. That centralized approach, potentially costly, potentially introduces latency, or you can use client-side load balancing. Again, with the server side, you're using things like accessing via sort of predetermined names, the conventions, API internal, pretty effective. I've ran systems like this, but it's not as good as client-side, because with client-side, you can sort of think about things deeper. You can implement things using that service mesh. Again, I don't need to think about it. I don't want to worry about load balancing. It's not delivering me features. I just want it to happen. It obviously relies on the service registry. Again, these are concepts that a couple of years ago I would talk to you until you were blue in the face about. But I truly believe that when you start looking at the more modern capabilities and the way that the software market's going and heading towards service mesh, trust me, it's not buzz. It saves you a kind of a lot of effort. And a lot of these concepts we don't need to worry about. We're dealing with a much higher layer of abstraction.
So let's
Should we
make
see
this
if it
work.
works?
Yeah, hope so. Okay, so let's make this one a lot bigger. So we can just use kubectl. Since we're running on Kubernetes, it's very easy to scale up the pods. We can just update the number of replicas from 0 to 1. There we go. From 1 to 6. And we should have 6 pods running. So let's apply that configuration. And then if we look back over here, we now see we have a lot of API pods running, right? So that should stop Nick from killing our beautiful Emojify application.
Well, as you can see, the buttons are lighting up on the Whacker pod here, which means that your users have noticed that you've got more instances. What are they going to do? Well, they're going to start trying to kill them. And they're doing a successful job in this. So how does this affect the overall health of the application now? Well, you're going to end up with transient failure, and this is a key thing. The website is going to be up for a number of users, but it's not going to be up for everybody. You can see the errors there. You can see the difference between the total requests. We're getting sort of errors coming in. I'm going to keep on killing those pods because this is fun. But there are things that we can do, which is quite straightforward, to be able to sort of transform this situation, to be able to buy us time. Because, I'm going to say this a number of times, but a fault in your system is not something that you should deal with reliability patterns. A reliability pattern buys you time until you fix a problem. It protects the end user. It doesn't protect you as an operator or a developer. So number one, the simplest thing that you can do is just retry connections. If I've got multiple instances of a pod, if I achieve failure, I should just retry it. And retries work in exactly that. An unhealthy service, you hit that endpoint, you just try another in the list. If I've got 6 endpoints in the list, I can keep retrying until I find a healthy one. It's a very sort of crude but effective mechanism of sort of dealing with this type of problem.
So let's implement this. So since we're using Ambassador to do our API gateway, and it'll handle the north to south traffic, we can actually use custom resource definitions of Ambassador to configure the retry policies of our application.
And I think that's key as well, that what we're doing here all along is reproducible. We're not just tweaking a setting somewhere in a UI. All of these steps, it's versionable. It's infrastructure as code. And that is, again, a really important factor when it comes to reliability. Always have the ability to get back to a known state and to be able to see the changes that you're making to the system.
Yeah, we really needed that this morning, and it worked perfectly.
We've tested it.
Yeah. So here we define a retry policy. So on every 500 range error, we will actually retry every 10 seconds, and we'll do 20 attempts to try and resolve the request. So let's apply this configuration to our cluster. Right, there we go. We have now the console API mapping configured. And if we refresh oh wait, the proxy died. Let me find where I put that one.
That's Kubernetes. Drink.
Yeah. That wasn't me. I didn't score a point on the pepcat counter. There we go. So if we look here, we now see that Ambassador configured our upstream correctly and added the retries to the application. So now if Nick would kill the applications, we should see retries show up in Grafana. So in this graph down here, we will actually see the number of retries come in, as I'm guessing they'll be orange, but you never know with Grafana.
That's
and we should not see errors. Sorry?
Would anybody else like to press a button? You look like you want to press a button.
Oh, they start coming in here. So we see that we have 10 retries, but we didn't get any errors to the end user. So that means that, yes, things were failing, but the end user did not notice it.
So 2 important things here. This chart, those retries, put alerts, get monitoring on those retries, on the retries. A retry is your early warning. It is avoiding that uncomfortable phone call with the pointy head boss. It buys you the time to fix the problem before your end user experiences the problem. Don't do what I used to do, which is use the end user as your monitoring. I'm going to put this down because I'm done with this now.
Really? Are you? Fine. We can automate that.
But again, retries, not the only pattern. You've got to think about these things in combination. We need to think about things like, what do you do in the instance of a timeout? Why is a timeout important? Well, the analogy that I was trying to come up with, which was admittedly not a particularly great one. Think about a timeout or a fault in a service as a blocked pipe. So with a blocked pipe, what happens is the water will not get through the pipe properly. It ends up backing up. And then you end up with a situation where you end up with a lot of unpleasant material in your bathroom floor. What a timeout will do is it won't protect you from the pipe getting blocked. It will protect you from the unpleasant material getting on your bathroom floor because you're protecting the back pressure in the system. There's a concept called cascading failure, and cascading failure is often caused by an area of the system failing, and that back pressure causes delays in other areas of the system and completely takes everything out. A timeout, think of it like a pressure valve. It releases the pressure in the area. It doesn't stop the fault, but it protects the other areas of the system. How do you set timeouts? It's difficult, but again, back on that observability. 99 percentiles are a really good place to start. That's kind of the area where 1% of your requests, the average duration, they're generally sort of seen as the anomalies. Again, you've got to use load testing. Every time you implement reliability, you've got to do it with load testing. You can load test in your production system if you're brave. And in fact, we used to do just that. We would load test on our production system out of hours when it would have limited customer impact. But we were predominantly a system which would run with users between about 7 and 11 p.m. Again, retries, timeouts, they change as the system changes. Don't just think about it as a one-shot. You've got to continually do things. You want to see that running?
Yep.
So what we've done, which is another, I think, a useful way of doing this, but we've got an ability to inject errors into a system deliberately.
Yes.
And Eric can explain that.
So what we're actually doing is Nick coded into the API application that we can introduce either delays or on purposely throwing like 500 errors. So in this case, what we're doing is every 20% of the requests, we will actually introduce a delay of 120 seconds, which will be longer than the normal request time, and actually it will time out. So we're introducing timeouts on purpose for this demo. So that's why Nick doesn't have to do the buttons anymore.
There's a lot of really sophisticated technology emerging now, which allows you to do things like fault injection. Like Envoy as a proxy has got that capability, but the configuration is still somewhat awkward. Over the next couple of years, I think we're going to see some really amazing kind of features around being able to manually inject faults, because simulating failure is a really good way to tune and protect against it.
Yeah. So we've actually defined 3 timeouts for this demo. We have the overall timeout for the request time, which we've put to 60 seconds, because we're doing the retry, so we don't want it to time out while we're retrying. And then there's the idle timeout, how long we want to keep the connections open once there is a properly connected client. And then we also want to set a timeout on how long we allow the client to wait for a connection to happen, which is, in this case, only 1 second, because everything's located together and it should happen very fast. So I've just applied that configuration that you just saw, and we can now actually see the effects in Grafana. So while we were applying this and the configuration was being distributed by Ambassador, we got some errors, but then they've died off, and we can see actually the retries happening. And we can see the timeouts happening as well.
So the initial errors you're seeing is due to something that we haven't done, which is we're not doing proper rolling updates inside of our cluster. We're being a little bit lazy and cutting some corners.
Present the box.
But you could see it there. You see that the system pressure is being reduced. The timeouts are active. Again, monitoring. I can see that's happening inside of my system. Retries, timeouts. Make sure you've got alerts for these things. They're your early warning system. The key thing about a timeout is a timeout in isolation is good, but why are you getting the timeout? Are you getting the timeout because the system in general is broken, or is a particular instance just busy? And the next pattern that we're going to look at, we'll kind of look at some of those things.
Yeah, I think it's important to point out that you can see that the number of requests we're serving is actually going down, but that's due to our application injecting the timeouts themselves. So the applications are just waiting longer themselves before they return. So normally it would not actually impact your throughput.
Your users will not be as gracious to you. Outlier detection. So this, again, we're leveling things up. So what we're doing now is we're saying, if there's an anomaly, is it a permanent anomaly or is it a transient failure? Most of the time, it's going to be a transient failure. So what do you want to do about that? Well, if you're having a service which is just slow, it's not completely broken, it's just running slow. What you don't want to do is apply more pressure to it. Because if you apply more pressure to it, you're going to compound the problem. You're going to make it worse. So with the outlier detection pattern, what you can do is you can say, well, hey, if a service is running slow, if it's returning a number of errors, what I want to do is I want to just take it out of my rotational pool, and I want to just allow it to recover on its own, and I will continue. Removing the pressure, and a lot of times, will be enough to be able for a service to recover. And the outlier detection pattern does just that. So is the request okay? Yeah, okay, return the response. Did I get an error? Is that error greater than the configuration of my fault tolerance? Take it out of the clustered pool. And we can show that with a little demo. Now, we're going to cheat a little bit on this demo because we've had to speed up the video. It takes a reasonable bit of time, but let's show you how that works.
Come on, internet. It's the worst that actually the live demos happen, but then when you have a video, it doesn't.
I've never had a video fail in a demo before. Is that a first?
It is for me.
What do you do as a backup for a video? Paper?
I guess we might have to.
Moving along, I think.
Yeah.
You can put that as a first. We're the only people who have ever had a video fail in a demo.
I think I can get around it, Nick. No, I can't. Never mind.
Yeah. Awkward silence.
Yes.
All right, let's go back to the live demo, which will probably work. I can share that with you in slides, but ultimately what I was going to show is that, again, you can see that when the errors are occurring, the endpoint is removed from the system. An outlier detection doesn't just work on a single sort of interval. It will bring back a service. Again, if it continues to fail, you remove the service for longer and longer periods, so it's an exponential removal. The key thing is we are giving recovery time to a service. We don't want to just kill it. You know, this is health checks. You've got to be careful with health checks, because health checks can fail just because the service is busy and is slow. You end up with a lot of gray failures. So I mentioned earlier it's all about layering. And don't use these patterns in isolation. You layer them up. You use your tryouts, your retries, your outlier detection, your circuit breaking. You layer these things up because they're designed to work in combination. And again, do this as a scientific approach. Load test, performance test your system. Don't just blindly make these configurations because you're potentially going to make things worse. But finally, we just want to look at geodistribution. What do you do when things really go wrong? So geodistribution, like, hey, why do I need multiple clusters? Why do I need multiple clouds? It depends. 5 nines uptime, what does that mean in real terms? 5.26 minutes of downtime per year. For me, if Emojify is down for 5.26 minutes, I don't mind. If I'm Visa, MasterCard, PayPal, if I'm processing the world's financial transactions, 5.26 minutes matters. And the key thing is around that 5.26 minutes or that 5 nines, it's an SLA. And having an SLA or a service level agreement does not mean that the service level agreement will be broken. And we've seen recently with sort of the outages at Google that you can have outages in a cloud for a number of days. And like, Google are not the only cloud. Every major cloud has had an outage recently, and they will potentially continue to do so. It's complicated technology. So some companies think, well, I need to use multiple clouds. I need to be able to have availability across cloud. Or maybe you've merged. One organization's using Azure, the other part of the organization's using GCP or AWS. Again, there are reasons why you might end up with multiple clouds. The cons to them, well, it's pretty expensive. It's incredibly difficult to operate, and most applications are stateful and will make it really difficult to kind of distribute across multiple clouds. So I would say avoid them if you can, but unfortunately, sometimes you can't. So how do you handle it? So what you do is you have a setup like this. We have our user in Holland here, and I apologize for the photograph, but I can honestly... So let me tell you a story. So we were sitting around at dinner last night, and I was like, what image can I use to represent Holland? And my buddy and colleague Tom said, oh, have you seen the Rotterdam gnome? I was like, no. He said, caveat, it's not safe for work. So I Googled it. That photo is not going up there. But I encourage you all to Google it. Rotterdam gnome. On your own phones. But anyway, what we want to do is thinking about things like geographic distribution. Multiple clusters, multiple regions. There is latency around the world. If I'm in Amsterdam and I'm hitting a server in the west coast of the USA, I'm going to get latency. It may be minimal, but there are statistical proof, certainly around e-commerce, that latency has a direct relationship to customer spend. So in some instances, it's really, really important. So I can use a system like Cloudflare, and Cloudflare is an external load balancer and CDN. It's operating outside of my cloud. And Cloudflare can load balance the traffic to each of my Kubernetes clusters. I've got one in DigitalOcean in Amsterdam, and I've got one in GCP in the west of the USA. So if Eric is in Amsterdam, he's always going to hit DigitalOcean in Amsterdam because we've got geographic routing, which is going to handle that for us. We're routing users to the lowest latency, but it also gives us the capability to burst. We can burst to other regions. We can follow the sun. We can scale down our clusters based on our geographic load. And specifically also, we can handle countrywide specifics, such as GDP, for sensitive data sort of holding and stuff like that. Let's have a look and see how that works.
OK. So right now, we're only running in Europe, in Amsterdam, and we're actually going to go towards a failover in the US. So in our Cloudflare setup, which we've already done, we've defined a pool for, down here, where is it? Maybe refresh. There we go. So we have a pool, one DigitalOcean, one GCP, but GCP is not up yet, so it's critical, and it's not serving any data because of that. So we're now going to spin up our GCP cluster. So I've defined the Emojify stack in Terraform, so I can apply it at once. And it'll just deploy all the deployments, all the components of Emojify API to our GCP setup. And I know all of you have this alias as well, right? TF YOLO.
You don't
apply everything, right? Fingers crossed. It's always scary when it's waiting.
This is that awkward silence, like when the site's going down.
It worked.
Thank you.
So, so it will now actually take 15 seconds because of the health check in Cloudflare for it to detect that GCP is healthy. So let's refresh, see if it noticed it. There we go. Everything is healthy. So we should now be able to go to the US version.
So we did just replicate our infrastructure in a completely different cloud, and it really was that easy. And we hadn't put a load of practice into making sure that worked for the demo. Honest.
So as you can see, at the top right, we have which cloud we're on right now, and we're on DigitalOcean, right? Let's refresh. We're in Spain, so obviously we're hitting DigitalOcean. So to easily test this, let's set up a VPN to the US, and then do a hard refresh.
So we got
and we are now using Google Cloud.
So why is this good? Well, we've literally just kind of shown it isn't that hard to do geo-distributed. But why? What are the benefits? Can you just bounce back to the slides there, buddy?
Yeah, just checking if we... Oh, that's a good one.
Oh, thank you. So Eric tries to mock me there, but that's actually my genuine amazement that his demo is working so far. Geo-distribution is useful in a number of terms, though. We can also think about this as terms of failover. So we can have multi-cluster, multi-cloud failover, active and passive, active and active. We're out of time, so let's quickly show how this works. I'm not just going to pick fun at the Dutch. I pick fun at myself, too. There's my queen. That's probably treason. You won't be seeing me next year. But the concept is that when you get a cloud failure, what you're automatically going to do is load balance out to another, to the hot standby or another passive. Let's see if we can make that work.
OK.
So Eric, as we mentioned earlier, is our PEBCAC aficionado. Could you scale up GCP to 10 instances for me, please?
Sure. So obviously, I'm not going to do that as code. I'm just going to do it immediately here. Right, let's find it. Replicas. 10, you said, right?
10. 10?
I did 10, didn't I? Oh.
10?
Well, I think it's still working.
10.
Right? I think Cloudflare cached it. Oh, wait. No, of course it's still working. The website's still up. Oh, that looks worse, though. Let me just get rid of the entire cloud. So maybe that'll fix it. So I'll just serve it from the US, like see if the failover actually works.
Just delete the whole cloud.
Yeah, well, that's what you do, right? You start over.
Slide 10. Eric Feld, PEBCAC aficionado.
Right? It's gone. Let's just start over from scratch, and it should all be fine. Oh, well, that's never good. So let's wait 15 seconds.
Give it time, 15 seconds. That's uncomfortable, 15 seconds.
OK. We're good.
I'm done. I'm really done. Thank you so much. Look.
Should we? Hold on.
Fist bump.
No, I'm just thinking
Uh-huh.
we could say Kubernetes a little bit more often.
Oh, Kubernetes. Drink. Come on.
Oh, yeah. No. Oh, well. Never mind. We'll work on that later.
Thanks.
Your clicker didn't work.
No. I completely forgot about the clicker.
Me too.
I completely forgot about the clicker because I normally use the Bluetooth version.
Guys, please.
Let's put this here.
Hello? Okay.
Yes. Hi.
Great talk. Thank you very much. I'm not an expert on distributed computing, so this might be completely wrong. You're basically saying initially retry, and I'm thinking, I've got a socket, I'm receiving packets, those are hardware interrupts, the load on the system is increasing. Some guy is retrying, and I'm still having coffee at the user space. My coffee is taking 2 seconds, and the guy is asking continually for another coffee.
Yeah.
Shit. That's the first thing that I'm thinking. The second thing that I'm thinking is, if I'm really busy at the bar, my first coffee takes 2 seconds. But there's somebody asking for more coffee, so it's taking 2.1 seconds, 2.2. So at least if you retry, please back off. Like, wait a little bit. What do you guys think about?
Yeah, so we didn't mention that, but you're absolutely right. So back off is a common pattern. So you would use something like an exponential back off with a retry. So the first retry might be immediate, the second one might be 2 seconds, the third one 4, 8, 16, et cetera, et cetera. And you do that exponentially because, again, it's about reducing back pressure. It very much depends on the number of failures you're experiencing and the capacity that you have within the system, but you're absolutely right. Great question there. When using retries, also look at exponential or other sort of back-off patterns.
Ricard, can I make a second question? Can you guys go to one slide where you had the service mesh architecture with control plane and data plane?
Hold on.
Oh, I'm sorry. Sorry. Fuck. I'll start a question.
No problem.
I can describe that slide through interpretive
No,
dance.
it's fine. You guys basically had a pod, there's the data plane that is talking to the app, and then on the top you had the control plane. And I always get scared when we talk about containers and VMs, because if this is a latency-sensitive application, how do I control the latency now that my data plane and my control plane are completely outside?
So in reality, the data plane is going to introduce latency, but it really isn't going to introduce a lot. So the application's talking to the data plane on the local host. So you've got that communication is happening inside of the kernel. The actual drop-off in performance is in the nature of microseconds. Where you introduce potentially some latency is if you're doing reliability based on layer 7, then the data plane has to understand layer 7. Now, obviously, layer 4 is just straight pass-through. But again, it's pros and cons. You know, I'm not saying that this is sort of a perfect pattern for every situation, but it's a sort of a pattern which is applicable to the majority of situations. Again, with the control plane and the service mesh, you can pick and choose. You can choose not to use reliability and to go straight L4 pass-through to get the maximum speed and efficiency and the lowest of latencies. But ordinarily, again, you're looking in terms of microseconds. If your API request takes 100 milliseconds and you're kind of dealing with fractions of that, it's potentially negligible. But great question. Thank you.
Plus, you can also mix and match the protocols. If some of your applications need high throughput, you could set the protocol to TCP, so it would not check the L7 HTTP headers, for instance. And then the services you really need it on, you could configure those to HTTP.
Any other questions? Anybody want to know how many PEBCAC points Eric has today? It's not a number that goes that big, right?
No, it doesn't.
Thank you so much for watching.